Okay, good morning, everyone. First of all, thanks a lot for joining this session on our new Dramix Pro software tool, which is now launched online globally. I see quite some familiar names and faces, which is nice to see. Also some new people, which I don't know. So all very welcome to attend this session. This is the second session of the day. So we already had a first session this morning in Asia and Australia. For those people who want to attend later, we also have a US time session later today. The idea today is that we want to give you a brief overview on steel fiber concrete and then how we can use them in flooring. So we will give a short overview on the types of floors that we can design with our software. And then most part of the session, I want to just give you some demonstrations on the tool and how we can use it and so on. There will be a Q&A available. So I have my colleague Daniel also in this call who will be moderating the Q&A. So easiest way, if you have any question, you can put it on the Q&A. At the end of the session, we can also allow for verbal questions if people want to do that. So I leave it up to you. But in the meantime, please feel free to use the Q&A to ask any question that you have. So then I suggest that we start. So again, on the agenda, I give you a short introduction about Bekaert, Dramix steel fiber concrete, how we go from a beam test to a bending moment capacity, the design fundamentals of steel fiber concrete, then the types of slabs on ground, and then a demo on some types of floors. For those people who don't know Bekaert yet, and I think most people will know us, but anyway, so as you might know, Bekaert is a steel wire company. Our main activities are steel wire transformation. Basically, we are sourcing wire rods. We are drawing it to whatever diameter is needed for a certain application. Can be up to 1 micron, which is much finer than a human hair. Plus, we also apply coating technologies. We apply coatings on wires. Can be just a color, can be a zinc coating, can be a very high-end coating. If we make the link with steel fibers, we also coat our fibers with zinc. So a galvanization of the fiber, mainly for instance, precast applications where we don't want to have corrosion on high-end surfaces of some high-end applications. Some numbers on Bekaert. So this is the numbers of 2023. We have a combined sales revenue of around 5 billion euros. 24,000 employees worldwide in 75 production plants. And you can see we have a very high focus on R&D and patenting. You see we have over 2,100 patents, which is a huge amount. Plus, also on a corporate level, we are putting high stresses on carbon reduction nowadays. This is a bit an idea on our footprint worldwide. So, in fact, there should be a Dramix plant close by every region nowadays. And so myself, I'm working for the building products division, as we call it. And there we have 4 different pillars. So just as a very short introduction, we have 4 big streams of products. The concrete reinforcement, which is mainly Dramix brand steel fibers, and also some synthetic fibers, macro and micro synthetic fibers. We also have some road asphalt reinforcement products under the name MeshTrack and FortiFix, which are interlaced to avoid reflective cracking to the asphalt surface. Some masonry reinforcement products under the name Murfor or Brickforce in the UK. And now also our Murfor Compact, which is the improved version with less losses and easier to carry, the Murfor Compact. And then we also have some plastering products. This as a very short introduction on Bekaert, on our company, on our applications. But today we want to talk about steel fiber concrete. So what is the principle of using fibers and reinforcement in general? Of course, fiber or concrete is a brittle material, has low tensile strength or nearly no tensile strength and low ductility. Which is why we want to add traditional reinforcement fibers or a combination of both. And the big advantage of fiber concrete is that we can go from a very brittle material, and by adding more and more fibers to the mix, to the concrete, we can end up with a very ductile, very predictable material, as you can see in this slide. Let me take a pointer also for the rest of the presentation. So you can see by adding more fibers, you will have much more cracks before you have an ultimate limit state failure. Plus, the advantage of fiber over rebar or unreinforced concrete is it's a three-dimensional reinforcement. It's in everywhere, it's in every direction, it's everywhere in the section, it's continuous, and you don't have a concrete cover. So also the fibers are at the top of the surface, which has, if you think about flooring, a very good impact on impact resistance, fatigue, and so on, because you are reinforcing the whole section. You don't have that 3, 4, 5, 6 centimeter unreinforced concrete, which is the concrete cover. So how are we now dealing with fiber concrete in our structural design? There are a lot of standards, norms, flooring documents available already nowadays to design concrete with. One of the mostly used ones are the Model Code 2010. Nowadays, we also have the new draft version of the Eurocode, where we have an Annex L, which is allowing us to design fiber concrete for structural applications. We also have ACI standards, and then we have some specific documents which are saying more about the applications, like, for instance, the TR34 for flooring, the CUR in the Netherlands for flooring, and so on and so on. But most of these have a bit the same stream. It all starts with the material characterization. So it's usually a beam test. Then come up with a constitutive law that we can use to have a sigma epsilon diagram. You have to also apply some design values for the applications. Could be some hyperstatic factors, some size factors, and then eventually you can end up with the moment capacity. Very similar also with punching, shear, and so on. For us in Europe, and I think most people here in the session are in Europe, the mostly used way of doing testing is with the EN beam, the EN 14651, which is basically a 3-point bending test. So 3-point bending test with a span of 500 millimeter, section 15 by 15 centimeter. And you make a saw cut in the middle. So you make a notch in the middle of the beam to make sure that you have a crack exactly in the middle, as we have a triangular shape of the bending moment capacity, or the occurring bending moments. And so what happens in that beam test, if you would not reinforce the beam, of course, you would have first a linear branch, you would have your failure, and then you have immediately failure until 0. The difference with steel fiber concrete is that we have a post-cracking capacity. So after the point of cracking, my capacity is not dropping to 0. It's a certain graph, depending on the concrete quality, depending on the fiber type, and depending on the fiber dosage. On this graph, usually we are identifying, in most standards, we are identifying 2 values, FR1 and FR3, we call it. FR1 is at a small deformation. CMOD is actually, you measure the opening of the saw cut. So CMOD of 0.5 is that the saw cut is opening with 0.5 millimeter. So you can imagine FR1 is at low deformations. It will be used more for SLS, serviceability limit state calculations. FR3 is more further down the line at higher deformation. So FR3 is more for ultimate limit state calculations. Typically, if we would do some beam tests and we do 6 beams, the coefficient of variation would be around 20 to 30%, which is in line with the section of the beam. But also in our calculation, we will take into account some upscale factors usually, because the variation on a small beam, which is only 15 by 15 centimeter in section, is much larger than in a large floor, which is, you could say, infinite in both directions. So in that case, we can also use an upscale factor again to go to the design values. I will not jump too much in the details of the different fiber types that we have at Bekaert, but I think many of you already know that we have three big families. We call them the 3D, 4D, and the 5D. And there's a very significant difference in behavior between the three fiber types, and there's also some difference in possible applications. 3D is the fiber type which is standard since the 70s already. 4D is the one which we have designed specifically to have an optimal crack control and SLS. And you can see this in this quite commercial graph, but this is close to reality. In fact, we see that the FR1 for the 4D is in fact the highest for the three different families. So you can imagine that the 4D fiber will be ideal for applications where not only ULS but also SLS is important, because as I mentioned, FR1 is the value that we will use in SLS calculations, crack width calculations, and so on. And then the 5D fiber, this is a very special fiber, in fact, because even at normal dosages, which is between 25 and 40 kilograms, I would say, even at normal dosages, we can reach already bending hardening behavior, which is very similar to what we achieve with the conventional reinforced concrete, which means also with the 5D fiber, we can do very structural applications. I will not jump too much into the details about the whole process to go to bending moment capacity, but I think it's important to understand also what's behind the tool here. As I explained, we have a material characteristic by testing, with beam testing. Every norm and standard, for instance, the new Eurocode, but also the model code, the German guideline, the RILEM, they give you then a sigma epsilon diagram, which is in fact our constitutive law that we can use. We apply some conversion factors. We, of course, apply some safety factors, some size factors, as I just explained, because we are having an infinite floor instead of only a very small beam, and sometimes even some hyperstatic factors, depending on the application. This is all done automatically in our tool, and these kind of factors. And then eventually, and then I think this is something that most of you, I think most of the people in the call here are engineers. Most of you will recognize this. So when you have a concrete element under bending, here you can see, for instance, the strains that you could have after cracking. And this is how it looks like under in tension. So you see, usually in the top, we have our compressive zone of the concrete. When we have only traditional rebar, then we will have our tension arrow here, where we have the rebar. The difference with fiber concrete is now that my full tension zone of my element is contributing to the bending moment. So under or below the neutral line here, we have the full tension zone, where we have steel fibers, which are now contributing to that balance and bending moment. And this is, again, of course, depending on that sigma 2, sigma 3, which is on its way, depending on the beam test values. And so very simply, we can go from a beam test over a constitutive law to a bending moment capacity. The tool will calculate these kind of diagrams automatically by when you add a certain thickness, a certain fiber type and dosage. So this is a very quick introduction in the fiber concrete as a material. I think here it's also important that we understand now steel fiber concrete and how it behaves in an element like a floor. There's a very significant difference between plain concrete, steel fiber concrete, and conventionally reinforced concrete. As I mentioned, plain concrete, before cracking, it's just linear, but after cracking, you have a brittle behavior and you don't have any post-cracking capacity left. For conventional concrete, so conventionally reinforced concrete, after the point of cracking, you have a bending hardening behavior, and you can always increase the load capacity, even in an isostatic beam. For steel fiber concrete, it can be somewhere in between. Depending on the fiber type, I have just shown you the difference between 3D, 4D, 5D. Can be bending softening or can be bending hardening. It depends on the fiber type and the dosage. And this is some extract from the model code, which I think is clearly showing what is now the difference between isostatic and hyperstatic, and how we can, even with a softening material, achieve a hardening system. Fibers are, or most fibers are softening in uniaxial tension. But as I explained, under bending, under isostatic bending, can be both softening and hardening. However, even with a softening material under bending, we can still achieve a hardening system, so a safe system which has a redistribution of bending moments available. I show you why later. But this is also very, I think this is a nice picture to show you what I mean now with isostatic and hyperstatic structure. An isostatic structure is a structure where the first crack is also the last crack usually. Yeah? So where we don't have any possibility of redistribution of bending moments. Imagine an isostatic beam, imagine a cantilever or this kind of system. If the chain or the wooden plank or the wall fails here, the ball will drop, which means that on a section level, if my section fails, my system fails, which means my system capacity is also my section capacity. This is very different to hyperstatic structures, where a floor on ground is also a hyperstatic structure. A hyperstatic structure, there it means if I would remove one of the beams, in this case for the Eiffel Tower, the forces would redistribute in the structure, and you could still improve the allowable load on that structure, which means system capacity can be larger than section capacity. And here I want to make the link with the floors, and this is the last technical part of the session. After that, I think will be more comprehensive, and we will dive more into the flooring types and the deminar. But this is to show you the difference between plain concrete and fiber concrete. So in plain concrete, if you would apply a load, you will have a certain bending moment in the floor. If I look into this section here, until I have crack in the section, my system is okay. But if I increase the load and I reach my first crack here under my loads, as I have seen in the beam test, my first crack means immediately my capacity drops down to 0. So which means that my bending moment line needs to shift up to a 0 capacity here, which also means that I will have immediate cracking on the top next to the load, and my system is failing immediately. This is very, very different with the steel fiber concrete, even if it's softening. Again, if I apply a load before cracking, nothing happens. On my system capacity here on the left side, I go up. But now, after my first crack, my capacity is not dropping to 0 anymore. My capacity is dropping to a certain value, which I have just explained, depending on the beam test. So this means that my red line is shifting up to the blue line, but it's not 0. So also on my system capacity, I can still increase my loads. And this process can even go further. So I can further increase my loads until I also would have cracking on the top of my slab. And then at the end, we will reach an ultimate limit failure. But so this is very simply to demonstrate that even with the softening material on section level, we can still achieve a hardening material or a hardening system. And this is very fundamental for the design with fiber concrete. So there's a difference between system performance and section performance. And this is also to make the link on how we have set up our tool. In fact, to determine occurring bending moments, we have two options. We can do a linear calculation with FEM or even manually, which is not considering redistribution of bending moments, which is very conservative, of course, because if I go back to the previous example, this would mean that my first crack would already be my failure, which I have just explained is not the case, because we have that possibility of redistribution of bending moments. So that's why in our tool we have programmed everything in a plastic way. So we have a plastic calculation, which is done by yield line theory. In our case here, we're using the yield line theory of Loosberg in our tool. So it's considering redistribution of bending moments and allows to fully use our steel fiber capacity, both having softening or bending hardening behavior. And this is then also, this is one of the examples how the formulas can look like, where we look, and you will see this in the tool. If we apply a point load here, we will always look at the system moment. So we will always look at M plus M prime. M is here under the load, and M prime is alongside the loads. And we will always look at the combination of both top and bottom bending moments. And we will compare that with the capacity top and bottom bending moments. So the yield line theory of Loosberg, it's an iterative plastic calculation method. There's many different parameters which are influencing here. One of the most fundamental ones are the soil characteristic, but also the geometry of the slab. The thicker the slab will be, the more it will attract bending moments, because it's always the most stiff element which is taking up the heaviest loads. All these formulas you will see also back in the printout of your design. This is not what I want to focus on here. And then I'm looking at the time here. Okay. One last introduction then to before we go to the tool, because I think it's also important to understand what type of floors we can now design with fiber concrete. The most typical type of floor that I believe all of you will know is a floor which has contraction joints. So here the idea is concrete, when you pour it in a large surface, it will shrink. If you're not doing anything, you will have some random cracking. So the idea is here that we are weakening some spots. We are weakening some locations with the saw cut. So we are usually making a saw cut of 1/3 of the total thickness of the slab, which is in fact telling to your slab you have to crack here and you have to crack in a straight line. Typically, this kind of floors, we will have saw cuts every 5 by 5 or 6 by 6 meters. Typically, we do it on the column grid. So usually we are making the saw cuts on the column grids. So the advantage here, it's very straightforward. It's very clean, cost effective, and it's very widely used. I think in almost every country in the world, this is standard practice. But there is also a downside to this kind of joints, mainly when we look at the long-term behavior of these joints. They can have some curling even very quickly after casting, but mainly also if you would have forklift with hard tires, a lot of movements in the slab, then you will have sooner or later some problems with cracking. That's why a second possibility to design floors is to use a jointless floor, as we call it in Bekaert. A jointless floor is in fact a floor which we can do also fiber only, where we are removing the saw cuts and we are making large panel castings. Large panel castings which are then separated from each other by armor joints, some metal prefabricated joints which are allowing to concentrate the shrinkage in that joint. So this is a typical commercially available joint. So the idea is here that all the shrinkage needs to be concentrated in the joint, and that in the rest of the slab, cracks are avoided. We are, in this case, also very depending on the friction of the floor and the subbase. So in these kind of applications, there are a lot of detailing we have to take into account. We have to make sure that we are isolating columns, that we put some extra reinforcement around the columns to avoid the crack on the corner. In some cases, we even put 2 plastic sheets underneath the floor to really reduce the friction and to really make sure that all the shrinkage can be concentrated in those joints. So this is already a second type of floors which we can design, and we can also design with the tool. So all of you will be able to do that with the new tool. We can even take it one step further. Some investors, they don't want to have any joint anymore. They don't want to have any socket, but they also don't want to have any opening armor joint anymore. In that case, we can opt for a seamless floor. So a seamless floor is removing both sockets and expansion joints. In this case, we are reaching the limit of fiber concrete only. As I have explained, fibers are strain softening. So at some point you will have a crack and you need to limit the crack width. In this case, we can do an active crack control by combining fibers and a top mesh. Usually a top mesh because we are mostly interested in avoiding large cracks at the surface. So in this case, the idea is that we want to have a lot of cracks, but they need to be small. This is not the scope of today because for this type of designs, you also need to do a separate crack width design. Aside from only looking at the ULS and looking into the loads, you need to do a separate design with another tool that we will make available in the coming months. So this one is to be will come in the coming months and will also be posted on our platform. So all of you will also be notified about that. Of course, in this type of floors, we also need some day joints sometimes because we cannot cast 10, 20, 100,000 square meter in one day. In that case, you can make a tie joint, which is just adding some extra reinforcement top and bottom at the location of the joint locally, and then you really keep it closed. So this is just a joint that you will see visually as a line on the surface, but it's not an opening joint. So this is a bit the conclusion of the type of floors that we can construct with fiber concrete or a combination. The socket floors, very simple, socket 6x6, the most common type of floor, the lowest initial investment, but on the long term can be more expensive. The jointless floor is somewhere in between. We are removing all the sockets. We have big panels of 30 by 30, 40 by 40 meters. Investment cost can be very similar to the socket floor because in a socket floor you have to take into account also the weak spots in your design. So even you could have a large point load on a socket, which could have an impact on the thickness. So typically with a jointless floor, we can go a bit thinner in thickness and can even be more economical than a socket floor in some cases. And then the seamless floor is, as I explained, it's unlimited. It can be 10, 20, 100,000 square meter without any opening joint, where we are combining rebar and fibers. So that's a very short introduction, but I think an important one to also understand what's now behind the software. Now I want to jump into the tool. We will send over the link later as well. But the tool is very easily accessible on our construction.bekaert.com website. So you can go to software tools there. You can go to Dramix Pro, discover the tool, and then you will have access. You have both the basic version, which is available for everyone. You can also apply for the advanced version, which has some more options in the calculation. You can also apply for the advanced one, and then we can also give this make this available to you. So now I want to make a first design to show you how we can use the tool. So we have just selected a typical project for this one. And let me start with a very simple socket floor. So imagine we have a warehouse where they have some pallet racking. Typically pallet racking, this is how it looks like. You have usually 2 racks back to back. Then you have an aisle. And then at the edge of the building, usually you only have one rack because you cannot reach the second one anymore. So typically what we have in this case is 4 points in line in the middle on the slab and 2 points in line at the edge of the slab. In this case, we take an example back-to-back distance, so 1,300, 1,000 millimeter. And usually you also have some columns at the edge. So the first point load at the edge, so this one here, usually is at least 300 millimeter away from the edge. Some other loads we want to take into account in this example. Some uniform loads could be some bulk loading, some ground loading, some pallets. A reached truck, in this case an FL3 according to Eurocode, which has a wheel load of 31.5 kilonewton and a wheel pressure of 5 megapascal. And for this example, we will also assume that there can be a truck driving inside and out of the building. So we will also take into account the lorry here. Typically, what we also need to know is what is my subbase? What does my subbase look like? What is the material of the subbase, and what is my performance of the subbase? There are many different testing methods available. In this case, we will work with plate bearing tests, so sub-base tests, which we call also the K-Westergaard. So in this particular example, we take 0.03 Newton per cubic millimeter, which is, I would say, the minimum. So in many standard and norms, this would be the minimum, because we know below that value, if you would drive in with the truck, you would already see the tracks of the truck in the subbase, which can already be a first crack at the end. So let us now look into the tool, how we can put this into the system. So I can create a project here. Just a second. Yeah, here I am. So I can create a project. You can also save projects. You can save your customers. So in this case, I will say a socket example. You can put it in a certain folder. You can say, look, this is the inside slab. You can say, what is my street, main street, Belgium, as this is where I am based right now. You can put in some remarks. You can also even put in a cover photo, which will be shown on the printout. Then you can give in your customer data. I will just give my own data here. And you can also say, okay, I want to have my own signature, my own information on the printout or not. So I will do in this case, yes. Then I can choose international system units or US system, and I can select my concrete code, which is now on EN, Europe. You need to save this always, and then you can go to the next page. Now, because this is the only tool that we make available online, is the slab-on-ground tool. The idea is that in the coming weeks, months, we will also make available a tool to design slab-on piles and a tool to design crack widths and so on. So in the future, more tools will appear here. But so for the moment, we are using the slab-on-ground tool. So this is how the tool is looking like. So it's, I can say, very intuitive. It's very straightforward. So on the settings page, we have some different settings we can enter here. Some approaches. These are in fact the different standards or guidelines we can use. One of the most commonly used ones internationally are, for instance, the TR34 or some other ones as well. We also have programmed our own Bekaert approach inside here, which is in many countries also the standard one and accepted in certifications. For instance, in Belgium, for people who are attending from Belgium, SECO has also approved the Bekaert standard way of working here. You can select your concrete age. Sometimes you want to do some check at 28 days usually, but it can be a bit shorter, a bit longer. You can select, of course, all your safety factors, where we have some default factors, which are coming again from the mostly used guidelines and norms, but you have the possibility to change it. Typically for fiber concrete and industrial floors on ground, we use 1.2 on the material, 1.5 for concrete, 1.5 for concrete in tension, 1.15 in steel. The long-term factors, then the load factors. Typically here we use 1.2 for the variable loads, which is also again related to the consequence class of a fiber concrete floor. A floor is not a structural element of the building. That's why the consequence class can be lower, and we can allow for a lower than typical safety factor. Then we can go to the structure. So I have already explained that there are different types of floor available. Here you can find them back. We have the socket floor, which I've explained, the jointless floor, and then the seamless floor, we call it the combi slab, combined reinforcement mesh and fibers. We also added screeds. Screeds are thin overlays, for instance, on an existing slab, and heavy duty pavements, which is a special type of socket slab, which I will also show as a second example or a third example. But in this case, our imaginary customer has asked for a socket floor, so we will make a socket design. Then slab exposure, indoor or outdoor, we have to select. The ambient conditions can be very cold, tempered, humid, and so on. You can also find back, not yet, but it will be here in the information, what is the difference. The ambient conditions are in fact influencing the socket opening. The larger my temperature difference, the more my socket can be open and the less I have interlocking of the aggregates in the socket. So my capacity in the socket will be less. So that's where it's important to also know a bit about the ambient conditions. So in this case, let's just put in some thickness because we don't know yet where we will end up with. I put in 15 centimeter. I put in a panel length, a socket length of 6 by 6 meter. And I can also give in my maximum panel ratio, so the length width ratio of my panel. In fact, we are not calculating with this one, but this is also to make it clear for the engineer and for the contractor that there is a limit here. We don't want to make a panel of 1 by 6 meter because then we will have the risk of some transversal cracking. Ideally, we have a square panel, so ideally it's 1. My recommendation would be try to limit it to 1.5 maximum. So if my socket distance in one direction would be 4, in the other direction I would not make it larger than 6, and so on. Then I can also select my types of joints. So in case of a socket floor, we could have maybe 2000 square meter casting per day. After 2000 square meter, maybe you could have a double profile. Could be the straight one, could be the sinus one or the wave one. We have many different types on the market. So I select that I will have this type of floor in my this type of joint in my floor, and I will also, of course, I will have sockets. The program will take some default values of the load transfer capacity of both the armor joint and the socket joint. Then I can also choose to select some auxiliary reinforcement, could be some local reinforcement at the edge or at the gateways. Now, initially, I will not do this, so I will just keep it fiber only now. And then last but not least, on the structure, I need to select my soil model. I have already explained, in this case, we have a K value of 0.03, so I can give this as an input. I can also work with other types of values. I can work with the multi-layer, with the E-moduluses of multi-layers. The program will always convert it into an equivalent K value. So we are always, in our yield line design, we are always going back to a K value. So we have a multi-layer, but we also have EV1, EV2 in many countries used. So you can give an EV1 and EV2 of the subbase, or you can also use with the CBR value. So all of them are available. We typically work with the subbase value. You even have the option to also include an insulation layer. So imagine a cold store, or even not a cold store, but in colder countries where we have an insulation everywhere. We can put in an insulation along the free edge, the first couple of meters, or everywhere. And there also you can put in the long-term K value of the insulation. This is typically available on the datasheet of the insulation supplier, but you can also estimate it quickly on dividing the long-term E-modulus of the insulation by the thickness of the insulation. In this case, I will remove the insulation because I'm not having it in my example. So now I have also entered my K value, and I can select also if there should be a separation layer or not. This is only textual. It's only to put some stress on that. It's not taking part of the design. And then I can make my design. So I have to select my concrete. You have the possibility to select the most commonly used concrete qualities here. So in my example here, it's an indoor floor. I think C2530 should be okay. Typically, in most countries, we go for 4D or 5D fibers, even though a softening fiber can be okay already from our system section capacity explanation that I have given. In most cases, it makes sense to go to the 4D fiber as it's more performant. It's cost more per kilogram, but as we can reduce the thickness compared to the 3D fiber, we see that we can be much more economical with the 4D fiber. Plus, you have a better behavior on the SLS, also on the crack control. So in this case, I select, maybe I will take a typical one that we use in Belgium a lot, 40-65-60, for instance. And I start with a dosage, which is 25 kilogram. Now I still need to enter my loads. So I will go to my loads. I have already explained for my loads, I have 4 points in line inside the slab, and I have 2 points in line at the edge of the slab. So I can start with the 4 points in line. In our example, 30 kilonewton. So my F1, my left rack is 30 kilonewton. My second rack, my point loads are also 30 kilonewton in my example. And then I can also put in my distance between my racking. So in my example, I chose 1000 millimeter, then 300 millimeter for the B for the back-to-back distance, and then C again 1000 millimeter. And then I have my foot plates, which are important not only for bending moment, but also for my punching check. I take 1000 by 100, 100 by 100 millimeter. Now I still need to select my location. So I have this load case, 4 points in line. Now I have to select here on my scheme, where do I want to put my loads? So the one that I have already selected here is in the middle of a panel. So the blue line here is the saw cut, which is my joint type 2 I have given in. The black line is joint type 1, which is the double profile, the armor joint. But so if you want to have full flexibility in your design, then I want to have my loads everywhere. Can be in the slab middle, can be on the joint, both perpendicular or parallel. Can also be on my dilatation joint or my armor joints. Can be on the corner or two sockets. In fact, cannot be on the edge, because the full load will never appear completely at the edge. For that, I will go to my 2-point loads, because if I have my 2-point loads, again, 30 kilonewton, again, distance 1000 millimeter, foot plate 100 by 100. In this case, we only have it when it's perpendicular to the edge of the slab, as I have shown here. So we only have the 2-point loads perpendicular to the edge of the slab. Where I can also select now, I have selected my load position. I can say to the program that there's a minimum distance of 300 millimeter between the edge of the slab and my first point loads. So that's all okay for my point loads. Now I can go to my wheel loads. So I have explained we have both a forklift and a truck. So my forklift, I had 31.5 kilonewton per wheel. I had a distance between the two wheels of 1000 millimeter. And I have a wheel pressure, because this is a hard volcanic tire, typically 5 MPa or more, 5 bar or more. In this case, we assume that the forklift can drive everywhere, can drive in the middle, can drive on the sockets, can drive on the armor joints, can even drive in or out of the building. So can even surpass the edge of the slab. So in this case, for instance, if you have a gate, which is going outside or to the next building, the forklift can drive inside and out. And then we also had the truck. So the truck where we had 4 wheels, so 2 wheels left, 2 wheels right. And we had quite a heavy axle load, 190 kilonewton, which means 47.5 kilonewton per wheel. And we have a wheel pressure of 2 MPa. So that one we can also very easily put in here. So 47.5. The distance between the wheels is 440 1,500, 440. This is a typical one from the Eurocode 0. And then my wheel pressure for this one, typically we take, for instance, 2 MPa, 2 bar in the wheel and the tires. Also here, I will assume that the truck can drive everywhere. We can assume that the truck can drive everywhere in the building and can also, of course, enter the building via the gates. And then, and that's the last one that we still have to enter, it's my uniform load. For the uniform load, we also have 3 different options. We can put in a worst case, a strip pattern uniform load, which is worst case for my bending moment. Because as you can imagine, if you would put a uniform load on the whole surface of the floor, it would not imply large bending moments. So we always try to look into the worst case if we don't have any information. But sometimes you do have the information. Huh? Sometimes you know it's, for instance, a bulk loading, which is a very big pile of for instance, aggregates. In that case, you could even select, okay, I have this uniform load and I have this load width. Or you can also say, I know exactly, for instance, if you have a steel coil warehouse, you know exactly in which rows you will have uniform loads. Then you can also put it this way manually. If not, I would recommend, if you don't have the information, assume that it can be worst case, that it will be worst case for my bending moments. So in this case, my example, I take into account 3 tons per square meter, 30 kilonewton per square meter. So if I'm correct, now we have put in all the information. And now what we can do already quickly, we can do a calculation of the interim results. Usually this one should go quite quickly. Depends if my connection is okay. So now we see there is a problem. No result check input. And I already see I have a unity check field here. Point loads are okay, but my wheel loads are 111%. And now you could do 2 things. You could simply increase the thickness without thinking, or we could look into a more pragmatic design. So that's why I will first calculate the final results to see a bit where is my problem. So now again, you don't have any results. You see, this is my overall conclusion. I have my different load types, and I see bending, shear, bending, shear, punching, and soil. We are checking all these. And I see there is an error with the bending for the wheel loads. So then I can look into the detail field here. I go to wheel loads, and I see my 2 wheel loads I have selected. So the 1 axle with 2 wheels and the 1 axle with 4 wheels. And I see there is an error only for one particular case where my truck, the 4 wheels, are parallel to the free edge. So in fact, where my truck is driving in and out of the building, that's the only location where I have a problem. So in this case, and this is what I like a lot about the tool, you know exactly what you can do to solve this. For that, I can go back to structure now. And as I already explained, I can put in auxiliary reinforcement. So I can say I will put in a top reinforcement extra, maybe even only a diameter 6, 150, and I can put it at the gateways. So the gateways where the truck is driving in and out of the building, that's where I can put in extra reinforcements. I need to check. My thickness has shifted. That's something we are still working on. My fiber type was this one, 25 kilogram. So now I have put in that extra reinforcement, and I can do the calculation again. And you see my problem is solved. My problem is solved. I have 89% unity check. I can go next, and now I can make a printout. I can make a summary printout. I can make an extended printout and a complete printout. I will show you the printout later. You can just print it, and then it will appear on your home page. So this is the first example where my solution now is this one. So my solution is 15 centimeter. Oh, I swap. 15 centimeter C25, 25 kilogram of 4D fiber, and we put an extra mesh at the gates where also my design node will show me what should be the size of the mesh I put in there. Look into the timing that we have a lot of time for questions. Okay. So second example I want to give you is a jointless floor. Very similar, but here we will have a bit of higher point load, 120 kilonewton. We have a higher uniform load, 50 kilonewton, and a higher forklift. Further than the rest, I don't have too many differences, aside also that I have a higher sub-base value. In this case, it's very similar. I will use the same example here. I go back. So here in this case, in the structure page, we can go to jointless floor. Jointless floor, and I will put it on fiber only again, which is correct. Let's start with 180 millimeter. And here in this case, now I have to put in a panel length. And if I try to put in, for instance, 6 meter, my program will protest. My program says to me, okay, jointless floor, for us, it's minimum 15 meter by 15 meter. Typically, it will be larger than that. So in this case, let's assume that we have a building where we can make panels 40 by 40 meter. Depending on my thickness and my panel length, my program will also give me a minimum dosage in function of the fiber type that you have selected. So in this case, I don't have any socket joint anymore. I only have the dovelled profile. I can change my sub-base value to 0.05 Newton per cubic millimeter again. I go to materials. In this case, let me look what I would like to put in. Let's stay with the C25 concrete. Let's maybe go to a more high-end fiber, which is the 408060 BGE. And let's look into, let's start with 25 kilogram as well to see if we can end up anywhere. Then on the loads, I can just quickly change my loads here. My point load, it's a bit higher. It's 120 kilonewton. Change to 119. We put 120 kilonewton again. My distance between the back-to-back racking is the same. My base plate, I take a bit larger. I take 120 by 120. Oh, no, this is the distance between. I take 120 by 20 for the foot plates. I do the same for my 2 points in line here. I take 120 by 120. Okay. Then I can go to the reloads as well. Let me only look into a forklift. So let me put the heavier forklift, which was an FL4, 45 kilonewton wheel load with a wheel distance of 1,200 and a wheel pressure of 5 MPa. And this one, we assume that it can also drive everywhere. You see, I cannot select the socket anymore here because I have a jointless floor. By default, I don't have any sockets. That's why I cannot select the boxes where the wheels are on the sockets, which makes sense. And then my uniform load, I select 50 kilonewton. Maybe in this case, yeah, we can put it again, worst case. Let me calculate the result now. Now the program will also check if my dosage is in line with my thickness and my panel size. So if it would not be the case, then it would not work. So in this case, in fact, the design is already passing. You see, my point loads are governing, which was to be expected because the point loads were 12 ton per point. And the governing one is bending. So if I look, where is my bending? In fact, in this case, bending at the edge is 95%. So imagine that this one would be 100%. Then you could even increase the thickness at the edge, or you could put a local reinforcement at the edge only and keep it at 18 centimeter. So again, you can make a printout here, summary or complete. And then one last example I want to show you is for an outdoor pavement. port pavements or airport pavement, or even just a truck parking area. But in this case, I want to do a reach stacker and container loads. So typically, reach stacker, those are very heavy beasts. They have a 100+ ton axle, in this case 110 ton on the front axle, 4 wheels, and then I assume in this case 4 containers stacked on top of each other with a point load of 75 kilonewton per foot plate. Typically in this kind of applications, we will use dovels in the sockets because we have this very heavy reach stacker driving around, and the reach stacker can have a big impact on the socket where the panels can start working separately. So in that case, typically we would add dovels, which is also one of the options I want to show you in the tool. And this can be both in the socket, but also in the other direction. So this is the one for the sockets. This is the one in the longitudinal joint. Can be both with a concrete paver or can be manually casted in. So, because this is something I also want to show you that this is possible. I go back to my example here. Next. In this case, what you can do, you can select the heavy duty pavement option.
Ben,
heavy
sorry
duty
to
pavement.
interrupt.
Yes.
We're not seeing the
I'm the wrong screen
the
again. Sorry.
With the tool.
Right.
Yep.
I share again. Thanks for notifying me.
Absolutely.
Should be better now.
Yes, it's back.
All right, and then I put this one again on the other screen. So now you see it back. But so as I have explained, heavy duty pavement, you can select it also here in the type of slab. In this case, typically it will be not 15 centimeter, will be usually a bit thicker. You can select again your panel size. In this case, what is the difference? You can also select in both directions dovelled joints. So my visualization is showing it already. I have a socket or a joint where there's a smooth dovell. As I explained here, you have a dovell every 5 or 5 by 5, 8 by 8 meter, whatever, which has a higher transfer capacity than only a socket. So, and in this case, we don't have any separation layer. I will go again for a 4D fiber. Typically, outdoor slabs, we will go for a higher concrete quality. So let's say C35 for an outdoor slab. Let's say maybe 30 kilogram of fibers. This is something you have to play with yourself. You will have to do it iteratively a bit on what is now my most optimal solution. But also here, what I can do, I can put in my point loads of my containers. Point loads of a container are typically 4 point loads in a rectangle. So 4 point loads in a rectangle. In my example, I had 75 kilonewton point loads, and I had a distance between the point loads, let's say, we can say 500 by 500 millimeter. That depends on every project. Typically, the footplate of a container is 170 by 170 in that order of magnitude. And in this case, I will assume that it can be positioned everywhere in the slab. I will not put it on the edge because typically my container, I will not completely put it on the edge of the slab. And then the only thing I need to add as well is the wheel loads. I have one axle with 4 wheels, as I have shown here. So I have my very heavy reach stacker, 4 wheels on the front axle with 110 ton divided by 4. So that one I can put in here. That should be 275 kilonewton. And I put in the distance. That is always depending on your data sheet, of course, of your truck. In this case, typically 2,400 in between the 2 wheel combination. And I have a wheel pressure of 1.5. And again, I can select all kinds of locations. This one, I will not assume that my reach stacker will be in the corner of the slab, and I can do my calculation. The final thing I want to show, and I think then we are nicely in time to have enough Q&A, is I want to guide you through the printout, because the printout is also giving you a lot of information. If you make a printout, you will see, and I go back to the homepage for that, you will always have your different projects here. And after you make the printout, you will be able to download it on over here. So if you push the arrow here, your tool will download the printout. I have already saved some of the printouts here in my folder to make it more quickly. Let me open the one for the jointless floor or the socket floor, for instance, this one. So this is typically what the printout will look like. So also if you make your own printouts, you can do this. As I have explained, you have the more basic one, or you have the very detailed one, as you want. This will then include your own data, your own name, your own contact details. You have a table of contents, some explanation about the different symbols we are using, which I will not go through now. Some information about the type of floor I have selected. So in this case, this is the one for the socket floor. So here my printout will explain, okay, what is the socket floor? This means that we make sockets every 5 by 5 meters and so on. Some information about the input. So slab type socket, indoor, 1 layer of PE foil, my thickness, my joint spacing, the type of joints that I have selected. So in this case, I have both dovelled profile and socket joints. My concrete quality, my maturity, fiber type and dosage. Testing according to the EN beam. Also extra reinforcement, as you remember, in this example, we have put in an extra rebar or an extra mesh at the gateways. Some information about the concrete, so the concrete properties. Fiber properties, so the tool is automatically taking into account the FR values which are corresponding with the input. So Bekaert has a huge database of testing values which are updated now and then by our concrete expertise center. And so here you can just use our database from Bekaert. Then some other typical values. This is all coming from the Eurocode, so no surprises here. My safety factors are explained here. If you would have any extra rebar or any extra reinforcement, you will have a schematic overview here on where it should be positioned and what are the sizes we need to put in. So in this case, I only have at the gate an extra mesh of 6/150, I think it was. And it says, okay, at least 1.5 meter in this direction and at least 1.5 meter alongside the gates. In general, no bottom reinforcement. It's a fiber-only solution in this case. Then my soil properties. So in fact, you see my design note is very similar to the input. It's really following the same flow. Soil properties, in this case, a K value of 0.003. No insulation layer selected. Then my program will calculate based on the thickness of the slab and the K value. It will calculate elastic length. The elastic length is one of the main parameters that we need in our yield line design. So the elastic line length will be determined here. And then also my maximum soil pressure will be determined based on the K value, because we also check if the soil or the insulation is not failing. If you put in an insulation, but my thickness of the insulation is too much or my stiffness is not enough, it could be that not the slab is failing, but the insulation is failing. So this is also something that is checked. Then my joints, I have 2 types of joints. I will not jump in the whole background here, but for both types, we are calculating a joint transfer capacity. For a dilatation joint or for the armor joint, we take a standard value. This is also something you can discuss with your joint supplier. What is the value we can take into account for a specific type of joints? And then, as I explained, for the socket, we will also calculate the efficiency of the sockets depending on my aggregate interlocking, which is again depending on my panel size and my temperature difference. So this is also calculated here. And then my schematic overview of I have both socket joints and armor joints. And then you have a whole table of all the inputs that you have done with respect to the loads. So where did I put in the loads? So I have put in 4-point loads. I have put in wheel loads, all the locations. This is something, I mean, you just read it yourself once, if you have time, then you will see how it looks like. My uniform load also, it will give me now, because I have selected worst case, it gives me now the geometry of the loads, where I have a block of first 3.2 meter loaded, 1.6 meter unloaded, and then 3.2 meter loaded. This is done iteratively by the program, so it checks what is my worst case scenario. And then, again, I will not jump into all the details here because then we don't have any time anymore, but it will calculate my, first of all, my bending moment capacity of my fiber reinforced slab. So based on what I have explained, based on the bending diagram here. So you see here for my fiber concrete, it's both top and bottom, it's 12 kilonewton meter per meter. And, you know, we also have a combined reinforcement at the edges, there it's 19.77. Now, it's also calculating then the occurring bending moments for all the load cases. So load case 1, 2, 3, 4, it will calculate a bit further down. It will calculate always my bending moment capacity. So you see it was in a table for every load case, you will see system occurring bending moment and system capacity. So that this is yield line design. We are always combining M plus M prime ED, and we compare it with M plus M line RD, resistance. And so on and so on. So these are all the different load cases. I will not show them all. Then you have a nice calculation overview with all the values on bending, the soil, the shear, and the punching. We have my absolute numbers, which is in fact very similar to the unity check that we have seen before in the tool. And then I have my conclusion. So here I have my conclusion of my solution, socket floor 15 centimeter, concrete quality, fibers type, and so on and so on. And then some remarks and some references. That brings me to the end of the presentation. I hope most of it is clear. And then I would say we jump to the questions, if there are any. I didn't see if there are any questions already came in. So maybe Daniel, if you can moderate if there is any questions now.
Right, so there was just one question regarding whether we will be sharing the recording of the webinar, which I believe we will, and we will send it, we will share it via email after the webinar this week, so tomorrow or Friday at the latest. And that is the only question so far. So I would like
see
to
another one coming in now.
We are very good, very good. Yeah, now there's questions are coming. So let me publish them so everyone can see them. And Ahmad Muhammad is asking if it would be possible to add an option to add auxiliary mesh around MEP provisions, openings in floor, if any, and around steel base plates, if any, as well.
Well, in this case, well, we don't have that option to have extra reinforcement at openings, but there you could use it. I mean, there you could use a pragmatic approach to consider it as an edge. So if you have a sizable opening, I'm not talking about a very small opening, but if you have a sizable opening in the slab, let's say 5 by 5 meter, where we don't have, where we have basically an edge. In that case, I would just consider that as an edge condition. Enter in the input. So you can say, okay, I have a load on that edge, and there in that case you can again add reinforcement on that particular zone. If it's more a specific hole in the slab, or maybe even a local a local area where we cannot really use the tool, then sometimes we need to use hand calculations as well. Sometimes if you have, for instance, a robot in the slab with a very high bending moment locally, then I would say we do a local check for that. And for that you can do yourself, but you can also rely on your Bekaert contact person locally to do that for you or help with you. So I hope that's answering the question.
And we have 2 more questions from Salah. Actually, 3 I see now. So let's start from the first one being, what is the minimum dosage of steel fiber for jointless and seamless floors?
Well, that's a question I cannot answer like that because first of all, it will depend on my thickness of the slab. Because the thicker your slab will be, the more you have a fiber section, basically. It also depends on the type. As you might know, we have different lengths, we have different diameters. So the thinner my fiber is, the more fiber I have per kilogram. But to answer somehow to that question, if we use a 4D 8060 type of fiber, which is 60 millimeter long and 0.75 millimeter diameter, I would say we'll start with 25 kilogram till 35 kilogram. That it will be in that range if we are talking about jointless floors. If we talk about seamless floors where we are combining fibers and mesh, we will end up somewhere between 20 and 30 kilogram typically for the seamless floors. But again, the tool will help you with that. The tool will help you with the minimum. I also would recommend you, depending on the country, depending on the concrete quality in the country, to also align with your local sales representative to see what is typically done in a certain country, because there might be some regional differences.
Thank you, Ben. Moving on to the next question, which is related to the Dramix Pro calculator tool itself. And the question is, what does system capacity mean in settings of the tool?
And system capacity, depending, and that depends a bit on which standard you are using. Sometimes the tool will calculate, for instance, in a cracked section with the fibers, but in some cases it will only take into account the plain concrete. In some other cases, depending on the standard. So if you are not changing that, I would say keep it by default, because then the tool will select already the combination of, in the bottom I take into account the fibers, in the top I only take into account plain concrete, or vice versa. If you do the default value, then it will do it automatically. But maybe for some reason you say, I want to calculate with fibers both top and bottom, or I want to calculate once now only with plain concrete. That's that. But honestly, this is one of the settings I would not touch too much. I would just keep it on the default value there. But that's where it's related to. Okay.
Okay, thank you. And final question from Salah is, what is the maximum panel ratio in jointless floors? Yeah.
Maximum, I would say 2. Depends a bit also on the absolute size of my slab, but as I mentioned before, preferably I would keep it below the 1.5. Below 1.5, we have very good experience that it works well. We also have experience with 1 to 2, but then you have to be very certain of all the boundary conditions, that the friction is very low, and so on and so on. So as a recommendation, I would say 1, but if you need to fit it into the building layout, let's try to limit to 1.5, I would say.
Very good. And then we have a new question from Nico from Unisol. How does the software handle the combination of rack feet and cartwheel together?
This one is not doing that. So the software is only taking into account separate loads or the 4 loads together. But as we are dealing with yield lines, usually this is even more conservative than the other way around. similar to, for instance, a racking load where you have a pallet load underneath the racking. When you have 4 points in line, you will have you could say like an oval yield line around the 4-point loads, which would be the failure mechanism. And in fact, if you would have a load close to that, a pallet load or a wheel load, in fact, my yield line surface will also change. And in almost all cases, it will be even an advantage. But if you would like to do a more advanced check where you have different point loads together, I would say use the point load option. If you have, for instance, 2 point loads and you want to see what is now my impact of another load next to it, I would just select the option where you have more point loads available, and I would add it manually as another point load to do the check. But honestly, we are not doing that checking.
All right, thank you, Ben. Another one from Peter. Can the software take into account prevented shrinkage due to, for example, the presence of foundation massive?
I think a very, very good question, and I hope I already touched a bit on that. For the socket floors and the jointless floors, the idea is that the shrinkage is all concentrated in the joints. So if you have a jointless floor, for instance, the idea is that we cannot have any fixed point in the slab. It should be free moving. So it's one of the conditions where we can do a jointless floor. For a combined solution, so a seamless floor where we combine top, mesh, and fibers, this is something we can do. There we can have some fixed points, some foundation massive, and so on. But we will need to do another calculation on the crack width. We need to do a calculation under restrained conditions. So we assume that the slab cannot move freely. And there we need to calculate the crack width, which is acceptable. Usually we will assume that we want to end up with 0.2, 0.3 millimeter. There we already have a tool available, which is not yet on this platform. This is an Excel tool that we have. But if you would be interested, we can do that tool for you now, or some of you might have the Excel tools from the past as well, which are the desktop tools. But this one, I mean, if you want to do that combination with the massives or with some connections, you need to do a crack width check where we can help you with to do that. But indeed, very, very valid question. I hope it answers a bit the question as well.
And currently, we seem we have run out of questions. If someone wants to ask directly, there are more coming. So let me publish them first. Another one from Nico. If the software can display panel center, panel corner, and panel edge constraints.
I think this is very similar to the question that we got from Peter Kleijs. I think the presence of foundation massive, if I understand it correctly, can we have panel edge constraints that you cannot add? So if you want to have constraint, if you want to have connections with some whatever fixed points, then you can use the tool that we have here just to make the ultimate limit state design. You will need to make a combined solution, mesh and fibers, and then in a second one, you will need to make a crack width design. I hope this is the same question. I'm not completely sure if this is answering your question, but I believe as you are mentioning constraints, this is similar.
Very good. And next question is from Nam, asking how the software can model the pyramid UDL load, for instance, a stockpile of aggregate on the floor.
Software cannot. We have to make some choices, and there I would say we need to use our engineering judgment to give in an input which is similar or which is representing closely the actual case. You can do it conservatively. You can maybe take like an average load between the top and the edge, but this is I would say the engineering judgment that you have to use, and you have to put in your uniform load. I would say one block with a certain width, which is similar to like a pyramid load. But this option we don't have, basically.
Yeah, there is one more from Francois. Are the values of load that you have to fill in design values, ULS, or characteristic values, SL?
Good question, Francois. It's SLS. So all the values that you put in are SLS values, and then the program will add dynamic factors, safety factors, and so on. So indeed, all the values that we are putting in are characteristic values.
All right, and looks like we got them all. We still have 8 minutes left, but
so then again, if there would be any further questions, I would like to refer you to our construction.bekaert.com website. There you will find much more about the tool. I think we will also post there the video about the webinar. We will also keep you updated on, you can subscribe to a newsletter. So if we will have the new tools available, we will also notify everyone that it's available. You can also find some other blogs, webinars, whatever there, and references may be also interesting. We have now a very nice map of the globe where you can see all types of references worldwide that could be useful for your client to show that it's not the first project ever with steel fiber concrete. So I would encourage you, if you have any question, you can have a look there, or you can reach out to your local sales representative or myself if you want. So then I just want to finish by thanking all of you to join. I think a nice attendance, and I hope that the tool is in the expectations. If you would have any feedback, anything, maybe some improvements, some options that you would like to include because you see it a lot in your market, you can always let us know, and then we can see if it makes sense to implement it or not. So everything there would be appreciated. Then I wish you all a good rest of the day. Thanks a lot for joining. And thank you, Daniel, for moderating.
absolutely. Thank you everyone for joining, and we'll be sending the recording later this week. Thank you, Ben. Have a great day,
All right.
everyone.
Bye-bye.